So, hello, welcome to this specialized lecture course on quantum gravity in the summer term 2022. So this is 2 hours per week. So we will have videos available that at least it's planned on Thursdays every week, should be online. And those of you who are familiar with it, with the earlier lecture courses, the early universe and general relativity, know how the procedure is. So every information that you need you will find on our homepage. You just go to the Gravity Group of Cologne and go to teaching, and there you find then the videos and all the rules and the literature. In addition to these videos, I plan to have a 1 hour extra session in presence. So that you can come, discuss with me, ask questions, and that we can discuss special issues. So I will not, in these 2 hour lectures, be able to give you many detailed calculations, because otherwise then we will not go very far. So for the lecture course, and this is in principle all you need to see, I give you, I hope, a concise and clear summary of the issues. And for technical details, I refer then either to the literature also or to this additional event in presence. And this additional event in presence starts next week, and it will take place on Thursdays at 11 o'clock. But the details are online. So for the Cologne students, you can use this for the module Relativity in Quantum Field Theory. It gives you 3 credit points, so there will be no extra exercises, but you can use it later together with other lecture courses in your oral exam, if you wish. Now, what should you know? I mean, to follow this course, of course, you can try to see whether you can follow, but I would expect that you need, of course, at least to have a quantum mechanics course, as you learn in the bachelor, but also Relativity 1 and 2. Yeah, so if you have not yet heard Relativity 1 and 2, my lectures on these topics are still online, so you can try to see them and whether you can follow them. And if you have no problems following them, I think you can also follow the quantum gravity course. Because I have given this lecture course before over many years, there is a book with the same title that I wrote, and the last edition that is available is from 2012. It's a 3rd edition. There will be maybe next year coming out a new edition, and at least from the Cologne network it's available online, and we also gave other references there. So please check the homepage for all the details. I will not repeat this here. Now, quantum gravity is not something that you usually learn in your studies, and this is of course for good reasons, because there is no agreed on theory of quantum gravity. Quantum gravity means a theory where the gravitational field is described by not a classical metric, but by a quantum theory or quantum field theory. So it's not yet available, and this has many reasons. First, it's difficult technically, you will learn that, but also it's difficult to check empirically because of the smallness of effects. So you might wonder why I offer a lecture on a theory that does not exist. And I hope I can motivate you to stay tuned, and will particularly devote 2 hours to this motivational chapter, which is also technically not so demanding. Why quantum gravity? So often I will use the acronym QG when I use quantum gravity, because this will of course often be written down. So then I will mainly focus on what we call quantum general relativity, which means that we take Einstein's theory, classical general relativity, as the correct theory of the classical gravitational field, and try to apply quantum rules to at least devise or guess a theory of quantum relativity, like we do quantum electrodynamics, for example. And you can do it in different ways, and one way is to do it in a what is called covariant way. So you use the four-dimensional metric, and typically you try to discuss a path integral of that. So this is done here. The alternative is what is done here in chapter 4, the Hamiltonian formalism of general relativity, and I use GR usually to denote general relativity, which is equivalent to this, but uses Hamiltonian and canonical coordinates p's and q's, as you're familiar with from quantum mechanics. I have here 1 hour here introduced parametrized and relational systems, which are not in particular gravitational systems, but simple systems which share many features of general relativity, so that you can learn here some conceptual issues that are also present here, but here the formalism is more complicated. Okay, in 5 then we finally quantize. Okay, covariant approaches also is a quantum. 3 and 4 are basically classical. Of course, I will also in 3 discuss some quantum issue, but 5 will then be the quantum version of that Hamiltonian formalism. And that's, I mean, the oldest canonical formalism that we have. I think I have forgotten here one to write down, namely the number 6. It depends, I mean, the Hamiltonian formalism depends on the variables you use, and the oldest one is just using the metric, because that's what in Einstein's theory. But you can use also other variables called connections and loops, and this is then here in 6, quantum gravity with connections and loops. So this is a formalism that is closer to Yang-Mills theory, and this is what is known as loop quantum gravity. Yeah, so that's it's already a lot of formalism, but so I mean here in these chapters 2 to 6, but I think it's unavoidable, and I try to be as clear as possible, and don't hesitate then to ask me in the extra lectures on Thursday if something remains unclear. Then 7 and 8 are basically applications. So laboratory effects, maybe they are there, but it's not yet clear whether they are big enough to test the theory. But it's believed that if they become relevant, they should be relevant for black holes and also for cosmology in the early universe. This is why we have these 2 chapters. And the last chapter, 9, is a conceptual summary and an outlook. So because we have also had to omit many issues. Yeah, so that's just the first, I would say, room that you enter when you open the door to the unknown here. As perhaps some of you notice, I have omitted string theory. This is not because I would not appreciate string theory as a candidate theory for quantum gravity. That is certainly not the case, but it would demand, I mean, of course, an extra couple of hours. And I know that in Bonn, courses are offered on string theory, so I can certainly recommend for those of you who are interested to go to these courses, or to follow the literature. In my book on quantum gravity, I have a chapter on string theory, at least a chapter on string theory as motivated by quantum gravity. There are also many other facets of string theory. And certainly I will make some remarks occasionally, for example, here about that. Yeah. So these are the 9 chapters, and I plan to have 12 lectures. So certainly I will have 2. I plan to have here 2. I mean, today and next week on this, and also here, because this is quite extended, I want to have 2 lectures, and also the quantum geometrodynamics. I want to have 2 lectures. Yeah. Okay. So that's for the overview. And then I think we can jump directly into the first chapter. And this is the motivational chapter. So first, why quantum gravity? It's mainly consists of two subjects. There's a third one, a brief third subsection that gives you also an outlook of what is to be done. And so the first subsection is 1.1, and it's called quantum theory and the gravitational field. Yeah, so quantum theory, if I use that, and I also like to have the acronym QT. Now, what is quantum theory? You're all familiar with quantum mechanics, and some of you are certainly familiar with quantum field theory. Now, what I consider as quantum theory is more a general framework for physical theories. It's not something that relates only to one interaction, like electromagnetism or weak interaction. So it's a general framework in our language in which we formulate physical theories. It seems to be universally valid, as much as we know. I mean, there have so far no contradiction to quantum theory. There's of course the ongoing debate about the interpretation, which we will cover at the end, but not about the formalism. And it's experimentally tested in unbelievable accuracy. So I could have a whole hour. I could just speak about the tests, up to applications in everyday life. Now, so quantum theory is a universal framework for physical theories. And okay, the gravitational field up to now is described very successfully by a classical theory. And this is Einstein's theory of general relativity, so successfully described by a classical theory. And this is GR. Of course, one can discuss classical generalizations of GR, and this is done, and this is important, but so far from the empirical point of view, it's not obvious that a more general classical theory is needed. And okay, this is what Einstein in 1915 had completed, and okay, what you learn in the relativity classes. John Wheeler preferred, instead of talking about general relativity, talk about geometrodynamics. Because the dynamical degrees of freedom are the geometric degrees of freedom, the metric, and so it's analogous to, say, electrodynamics, where the electric and magnetic field are the dynamical quantities. And in fact, I agree with John Wheeler, that would be a much better name for Einstein theory, but of course we have the historical accidents, and as you have learned in the general relativity classes, why Einstein, you have learned why he called it like that, and I will keep, of course, that name. As I said, all the observations seem to be in accordance with relativity. I mean, from the everyday life, which is the GPS system, for example, up to stars, galaxies, and cosmology. Of course, there are some puzzles still. I mean, you have learned about dark matter and dark energy, and it could well be that they point towards a generalization, both in the quantum and the classical direction. But it's not clear. I mean, it could well be that dark matter, for example, there's a new particle and it obeys the rules of general relativity, and that dark energy is maybe described by just a cosmological constant or by some field that is well accommodated into Einstein equation. That could well be. No? So one has to keep that in mind, and dark energy, dark matter, that they could maybe give you a key towards a generalization, but it's not obvious. Especially, of course, impressive is the direct detection of gravitational waves. What you know, I mean, 2015 was the first event that was recorded in the LIGO interferometers on Earth. I mean, the coalescence of two black holes in cosmological distances. And we have now ongoing detections in LIGO, Virgo, and there will be other detectors. Together, of course, with indirect tests that come from pulsars. There's also this idea, I mean, this pulsar timing array, so that perhaps even small and long waves, gravitational waves, can be seen via the clock running of the many pulsars in our galaxy. And we have very accurate clocks on Earth, and so eventually these measurements are only limited by the limits of these clocks. Now let me be a bit more precise. I mean, GR, we have the Einstein equations, and the Einstein equations, they come from the Einstein-Hilbert action that I write down again here for you. So in this standard way, I integrate over the four-dimensional region of the manifold R minus 2 lambda with the four-dimensional Ricci scalar and the cosmological constant. And for completeness, I add here a surface term minus c to the 4 over 8 pi g, and the integral over the boundary of the m d3x square root of h. Okay, now you will learn about these in particular in chapter 4. Let me now only mention here, this is the trace of the so-called second fundamental form, and this is the determinant of the three-dimensional metric, and this refers to the boundary. I mean, here I wrote it down for spatial boundaries, so you have here, say, the region of the four-dimensional manifold M, and here we have then here it corresponds, I mean, to time points, so temporal boundary. Of course, you can also have spatial boundaries here, then you have another sign. But the point is here, for the variational principle, it's very convenient to add this term. This is what Einstein already emphasized in 1916, because here this Ricci scalar has second derivatives of the metric, and for variational principle, recall mechanics, it's good to have, I mean, only first derivative. This can be accomplished here, not in general, but here, because the second derivatives occur linearly, and so we can make a partial integration to put them into a surface term. And if you just add the negative of that surface term, then the second derivatives are gone. So this here is just tailored in such a way that you only have first derivatives, no? And that's very convenient. Now this here is of course determined from the classical limit of GR, from the special relativity and Newtonian theory, and the speed of light has a certain constant and a gravitational constant. So c 4 over 16 pi g, okay, has a certain numerical value, 2.41 times 10 to the 47 gram centimeter over second squared. Or you can also write it as 2.29 times 10 to the 74. You have here centimeter times second to the minus 1 times h bar. Now, of course, we don't just have gravity, we also have matter of other fields, and so we have to add here another part. So the total action S is then the Einstein-Hilbert action plus the matter action Sm, and from here I calculate the T mu nu as minus 2 over square root of minus g, then the variational derivative with respect to g mu nu. Yeah. Okay, that's just what you know, and from this then by variation with respect to the metric we get the Einstein equations. So the Einstein tensor g mu nu is defined as r mu nu minus 1/2 g mu nu times r, and so the right hand side is 8 pi g over c to the 4 times t mu nu, and I add the cosmological constant term here on the right, which is the modern point of view. Einstein had it on the left hand side, but here the modern point of view is that this is somehow contributes to t mu nu as the vacuum energy, if you like. The conventions are the same as in my relativity class. They coincide with the convention used in the Misner-Son and Wheeler book, for example. So the metric, I mean, when I diagonalize the signature is minus 1, 1, 1, 1, and most of the time I restrict it to 4 space-time dimensions. There are theories that have higher dimensions, especially in string theory they are used, but I will not usually make use of them. Okay, so the conventions are such that r mu nu is r rho mu nu rho, r rho mu rho nu, so we sum over this and here the middle one, and so r mu nu alpha beta is with a plus sign, the alpha, the Christoffels, and so on. No? So look at Misner-Son and Wheeler, for example, if you are in doubt. Now, okay, when talking about general relativity, of course, there is a very slight generalization that I also discussed in the relativity class called the Einstein-Cartan theory. Now, the Einstein-Cartan theory is well motivated. It's if you view gravity from a gauge aspect, and if you have translations globally and Lorentz transformations, and you gauge them by using potentials, so you have tetrads and connections, and the field strengths are then torsion and curvature. So here, of course, in Einstein series we have curvature, but the torsion in Einstein theory is 0. Now, I motivated torsion in my relativity class, and also you may imagine here to discuss everything what follows with Einstein-Cartan instead of Einstein, but I will not do that, not because this is not interesting, but just to be, concrete and to discuss the simplest. The generalization is called actually Poincaré gauge theory. The one maybe, or the most important motivation is that there are fermions in nature, electrons. We consist of fermions, and they are described by the Dirac equation. And for the Dirac equation, the metric here is not sufficient. You have to go to use so-called tetrads to formulate it, and if you have them, you necessarily get torsion. So spin 1/2 generates torsion, and so you should not neglect that. The reason why it's often neglected is that the effects are very small, and it's not clear whether they can be really measured. But because of the presence of fermions, these effects are in principle there, and you should keep that in mind. People, and you will see that here, focus on, say, usually on special quantum properties of the gravitational field, and not so much on things that come from fermions. So as matter degrees of freedom, often scalar fields or vector fields are just used, and the torsion and the fermions are left for higher considerations. But keep in mind that they are important, and that at the final theory you should include them. Now, why quantum gravity? Why are not happy? I could say, okay, that's the state of the art, and we do not need more, and bye-bye. But there's, of course, a motivation, and of course I want to convince you to stay here with that lecture course, and that these motivations are real. So let me give the main motivations. Maybe it's not even a complete list. So the first motivation is the unification of all interactions. Yeah. You know from the history of physics that there is a very successful program called reductionism, so that you can combine theories that were previously considered to be in the 18th and beginning of 19th century as separate theories, but in the 19th century one has learned that they are actually part of the theory of electrodynamics. And we have also partly unified the electromagnetic interaction with certainly with the weak interaction, and the hope is also to include a strong interaction. Now, if one subscribes to that program, and it's not clear whether you have to, it could be wrong, but if you subscribe to that program, you would also want to include gravity, necessarily. But gravity stands apart here. So all the others, so-called standard model of particle physics is described by a quantum field theory, and the standard model of particle physics would somehow to be included here in this T mu nu in an appropriate version. I mean, of course, if it's quantum, it cannot stay there. And so if you want to couple it to gravity, you would also want, of course, gravity in the same framework. I mean, how can you make sense of a theory that is partly classical and partly quantum? It is possible to write down such theories. We will next time briefly mention it. But at least from this reductionism point of view, you would want to have one framework. Now, the second motivation is that GR is incomplete, and these are the so-called singularity theorems. Proven by Penrose. And his first theorem was from 65 with for the black holes, for which he had received the Nobel Prize, I mean, decades later in 2020. And then Hawking's cosmological theorems and also others by Geroch and so on. So, which means that GR is incomplete. And it's not just something esoteric. This incompleteness exhibits itself in interesting situations, namely in cosmology. I mean, the beginning of the universe is not described or cannot be described by GR, because what we call the Big Bang is something you have infinite quantities, but also the interior of black holes. This is why you see here in chapter 7 and 8 we focus on black holes and cosmology, because there actually we need something more general. A conceptual problem is what we call the problem of time. Of course, we all have problems of time, but what is meant here is, of course, a conceptual problem about the concept of time in physics. And you will learn about, I mean, this, there will be a classical version and a quantum version. So the classical version we'll discuss in chapter 4, and the quantum version in chapter 5. And it means that, in quantum theory, the dynamical quantities are all put into operators, transformed into operators. In quantum mechanics, you have the position operator and so on. Or in quantum field theory, you have, say, the electromagnetic field as operators. But time is left classical. No? So the T in the Schrödinger equation is Newton's absolute time, and in usual quantum field theory you have a Minkowski space-time as a classical background. And in relativity, of course, time is not absolute. It's part of space-time, and it's part of the four-dimensional metric G mu nu. So if you want to combine quantum theory with relativity, then, I mean, either time cannot at the same time stay absolute and become dynamical. So one has to think about that. So you perhaps know that Einstein arrived at his special theory of relativity in 1905 by a careful analysis of the concept of time, particularly what simultaneity and so means. And it could well be that the discussion of the concept of time also leads here to progress. Another point that is maybe in some sense related to B, but only in some sense, because there are also infinities of another type. Yeah? So here are infinities because of GR, but there are infinities that come from quantum field theory. Yeah? Every one of you who has even learned a bit about quantum field theory knows that there are, at the very beginning, you arrive at quantities that go to infinity. You have infinitely many harmonic oscillators, even for the free field, and that you have to do something that is called regularization and renormalization. But it could be that this has just to do with the microscopic structure of space-time. There maybe is not really a continuum, but a discrete structure of space-time, maybe a natural cut-off. And so decades ago already, by people like Pauli or Landau and others, they have speculated that divergence will disappear in a natural way if we include gravity. So the divergences of quantum field theory, so will they disappear? And yeah, the final motivation is a very general one. Well, there may be others, but this is what I have here listed, is just the application of the superposition principle. This is, at least for me, part of the definition of what the quantum theory means, that if you have, say, two quantum states, that you can add them up. Yeah? So that, I mean, if something can be here, a wave packet, and here you can add them up. So that's the superposition principle, which, as far as we know, is universally valid. Okay, there's this discussion about possible collapse of the wave function, but at least in all situations where you can do experiments here, the superposition principle is valid, and it's at the heart of the quantum theory. And as Feynman has, for example, argued in a contribution to a conference of 1957, one can also argue that superpositions are needed for the gravitational field. I mean, Feynman had here the Stern-Gerlach experiment or modification. So you have a beam, say, of silver atoms, whatever, that are deflected in an inhomogeneous gravitational field. So you have here a counter 1 and a counter 2. So if spin is up, maybe this makes click. If spin is down, this makes click. But of course, if spin is to the right or to the left, you have a superposition of the two. Now, Feynman envisaged that there is a connection to a macroscopic object, so a ball, say, that is deflected upward if this makes click, and deflected downward if this makes click. But what happens if you have a superposition of the two? So Feynman argues you will have a superposition of this going up and down. It's a bit like a Schrödinger cat, where you have all a macroscopic system being in a superposition, so microscopic arrangements. But this ball already has a measurable gravitational field. So if you put such a massive object in a superposition at different positions, so what happens with the respective gravitational fields? So you might expect they're also in a superposition. Or you have a new theory that violates the superposition principle, as for example Roger Penrose speculates that you have a new type of nonlinearity. That's possible, but most of the concrete approaches that we discussed, they keep this principle. Yeah, so even string theory. This is why we restrict to such approaches. Let me quote Feynman. I mean, the quote is also in the book. If you believe in quantum mechanics up to any level, then you have to believe in gravitational quantization in order to describe this experiment. It may turn out, since we've never done experiment at this level, that it's not possible, that there's something the matter with our quantum mechanics when we have too much action in the system or too much mass or something. But that is the only way I can see which would keep you from the necessity of quantizing the gravitational field. It's a way that I don't want to propose. No? So Feynman follows the standard line of argument that you have a linear theory. Okay, he developed, of course, the path integral formalism, which we learn about here, and which is, of course, implements the superposition principle at a central level. Okay, so the superposition principle is very general, but nevertheless, so it can be applied to any scale. So gravitational field, say you can superpose this and this here, and you have then a superposition of a gravitational field. But there is definitely a scale where quantum gravity effects should anyway be dominant. And this is the so-called Planck scale, and this is the scale that you find when combining the fundamental constants of nature, namely the speed of light, the gravitational constant, and the quantum of action, so Planck's constant h bar. Yeah, so what about the relevant scales? No, so you have these too often. It's here so symbolically represented in a diagram. C G here. You could say here, some people claim, okay, this partly conversion factor. So here, C is used to convert, I mean, between space and time. And we often said C equals 1 and measure everything in space. H is, if you like, a conversion between momenta and wavelengths, I mean, which follows from Louis de Broglie's relation. And you can say this is a conversion factor between curvature and energy momentum tensor. It's generally believed that, I mean, 3 units are sufficient to derive all other units. And this is what is done in the so-called CGS system, centimeter gram second system. Although, of course, our actually used system, the SI system, for practical reasons, uses more than 3 fundamental. Now, Planck introduced them already in 1899, actually 1 year before he officially introduced his quantum of action, which in 1900 he called H. So in 1899 it's called B, but it's still there. And if you want to know why he could do it earlier, maybe you come to the first lecture in presence, so I can tell you why this is done. I use modern notation, so we also used for the gravitational constant, you used F. For this, used B in 1899. Okay, only C was already used. And you can convince yourself, and please do that as a small exercise, that we can define the following quantities called the Planck length, the Planck time, and the Planck mass. And so we have here square root of h bar g over c cube, and this is LP over c, which is square root of h bar c over c to the 5, and this is h bar over LP times c is square root of h bar c over g. And if you insert here the values, and you find that this is around 1.62 times 10 to the minus 33 centimeter, which is the Planck length. And so this is around 5.40 times 10 to the minus 44 seconds, which is the Planck time. And this is around 2.17 times 10 to the minus 5 gram. Of course, you could also here use meters and kilogram, which is the Planck mass. Or you can write it also in terms of energy using E is mc squared, right? Then you can, particle physicists prefer to use the electron volt, so it's 1.22 times 10 to the 19 giga electron volts over c squared. Yeah, so you see, if you have the three, you can really construct lengths and times and masses, which you cannot do just with two of them. And they are unique up, of course, to some numerical factor that you may wish here to include, and which is sometimes done, some factor 8 pi or so on. One motivation to find them is, for example, if you go to a particle, elementary particle, and in quantum field theory, a typical scale is the Compton wavelength or the reduced Compton wavelengths, and in gravity a typical scale is the Schwarzschild radius if you have a massive particle. And if you consider when they are equal, so e.g. particle with mass m, so you have the Compton wavelengths, which is all reduced Compton wavelengths. Yeah, if you set this equal to the Schwarzschild radius, which is 2gm over c squared, then they are equal. If you forget this factor of 2, which is irrelevant, that if they are equal if m is of the order of the Planck mass. So if you have a Planck mass particle, Compton wavelengths and Schwarzschild radius coincide, which means that the curvature of this is no longer negligible. You cannot just pretend you are in flat quantum field theory because your Compton wavelength is already the Schwarzschild radius and there may be a black hole forming or whatever. So definitely you have to think about what to do with that. You can go on with that. Yeah. Some people define a Planck temperature, also a Planck density. Maybe I don't write this down here. It's in the book. But you can also have a Planck charge. That's not always discussed in the literature, Planck charge. So if you, charge in CGS unit, so the dimension of a charge, Q is electric charge, is a mass to the 1/2, length to the 3/2 over time t. Of course, you know from your classes this is Cologne, but in the CGS units you can derive it from meter seconds and or centimeter seconds and gram. And if you use here the Planck units here, then you get a Planck charge. So the Planck charge, Qp, you can then define as square root of mp times lp times lp over tp, which is found to be, if you insert here this value, square root of g times mp, and if you insert mp, then it's just square root of h bar times c. So there's no g here. No? So the Planck charge is independent of the gravitational constant. In fact, you can interpret this, if you have two objects that have Planck mass and they are electrically charged and have Planck charge, so there's certainly a repulsion, a Coulomb repulsion from the charges and a Newtonian attraction, but for these cases this just coincides. No? So here for this, so the Newtonian attraction is equal to the Coulombian repulsion. I should mention that since I think 2019 in the revised system of units of the SI system, so since 2019, so the original Planck constant, which is a 2 pi h bar and E and C, they are taken as exact numbers. So used to define, the mass and also the length. It's only the time it still comes from the clocks, from a certain transition, as you know, from between hyperstructure spectral lines. The gravitational constant cannot be used here because that's very, relatively poorly known concerning the accuracy, only to about accuracy of 10 to the minus 4. And what is precisely known is G times M, for example, M, the solar mass, but G itself, of course, you have these Cavendish balances and other things, and there are still inaccuracies. Let me briefly mention that if someone has done something, you often find another person who did the same thing earlier. Now Planck was only the first one having these Planck units, but the Irish physicist Stoney, George Johnston Stoney, who actually invented the name electron, and who lived from 1826 to 1911. He had similar units proposed in 1881. Of course, there was no idea at that time about the quantum of action, so what could he do? Well, instead of that, he used what we now call the fine structure constant, because of course electrostatics was known, and in modern terms we have alpha is E squared over h bar c. So if you have say excess on this, then indirectly you also have excess on this. So this is because this is around as you know 1 over 107. So his units differ from Planck's units by square roots of that. Yeah. So it's very interesting. It's a bit not so easy reading how he did that, but it's certainly worth mentioning. And okay, this is, of course, in a sense, much more modern and clear. So we have just introduced the relevant scales for quantum gravity, Planck scales, and as you have seen, they are very far away from everyday scales. 10 to the minus 33 centimeters. You cannot directly probe in accelerators. So even at CERN, the LHC, you can probe down to whatever, 10 to the minus 18 or so centimeters. Also the times 10 to the minus 44 seconds you cannot resolve in terrestrial experiments. But nevertheless, they are there, and they might become relevant, say, in extreme conditions like black holes or the early universe. Just let me mention that another reason, of course, why you usually don't learn about Planck scales in your standard courses, because if you look, say, in astrophysics at the relevant structures in the universe, they occur at scales that really have far remote from the Planck scales, and they actually occur at simple powers of another quantity, and this other quantity, let me introduce the structures in the universe. So, so they occur at simple powers of what is called alpha g, and some people call it fine structure constant of gravity. It's maybe not a good name, but it's defined as a dimensionless combination of the gravitational constant, the proton mass, and h bar and c. And if you recall, the definition of Planck mass, we have m proton over m Planck squared. No? So that's the squared ratio of the proton mass and the Planck mass, and this is a very small number. Now, the proton mass, of course, is what enters, say, much of standard physics. And if you learn about in astrophysics or in relativity about the Chandrasekhar mass, for example, then of course the proton mass is very important. So if you have, for example, the Chandrasekhar mass, MC, which is defined, or well, which is approximately, there are some factors, but alpha g to the minus 3/2 times the proton mass. No? So you see this is related very with a simple power here of alpha g to the proton mass. No? So this simple formula gives you about 1.8 solar masses. A more precise calculation gives here 1.44, but that's not my point. The point is that here this here determines the structures. I mean the Chandrasekhar mass, that's okay, the mass scale of white dwarfs, but also the mass scale of stars like our sun, which end up in a white dwarf. Also, for example, the the lifetime of main sequence stars. This means of the order. There are of course a lot of nasty details. Alpha g times minus 3/2 the same power times the Planck time, and so on. No? So you can do many estimates in astrophysics by just having such quantities, and here this alpha g is what is here. But where does alpha g come from? Yeah, of course you can insert a measured value of the proton mass, and you insert the Planck mass, and then it comes out. But why does it have that very small number? No? If it had much bigger, then the universe would look totally different. Now that's a puzzle. So where from? That's a big puzzle, and many people have speculated. And so the idea of a unified theory of all interactions, such as string theory, the idea was that one can calculate such numbers from fundamental principle. Say from the compactification of the string landscape, for whatever. There are many. You find many ideas in the literature, but there's no really, derivation yet that a satisfactory derivation that gives you MPR in terms of MP. One possibility could be that it's just not possible. Yeah, you cannot calculate, say, the orbits of the planets. The distance of the planets from the sun. It's just an accident that you have mass or that and so on. It could just be an accident, and it could be that the fundamental theory would give you also other possibilities. Then, of course, we are not so happy, because then we cannot understand more, or we have to use the so-called anthropic principle, or the fundamental theory allows us to calculate this. This would be a big success of the underlying theory. But then, of course, another question arises, then why this number is of such a value that it just gives the universe in such a way. So you see many fundamental questions that have to do with the unsolved problem also of quantum gravity of a fundamental theory. And this, of course, also holds for other, say, constants of the standard model. The standard model of particle physics has about 20 or so free parameters that you have to measure, but you cannot understand better. And so the question is, like with this here, can you derive them from a fundamental description, or they are just, in a sense, arbitrary, and they are just fixed in our world by a reason we don't understand. Now, the lecture course is about quantum gravity, which is a full quantization of the gravitational field. But before we enter that, which is then from chapter 2 on, let me discuss very briefly, with, say, details in the Thursday lecture, if desired, very briefly, the relation generally between quantum theory and gravity, even if gravity is left classical. And so the first level will be quantum mechanics and Newtonian gravity. The next level will then be quantum field theory in curved space-time. And the final level will be then the rest of the lecture, quantum gravity. No? So, distinguish different levels. Of the relation between quantum theory gravity. So on the first level is quantum mechanics, QM, and Newtonian gravity. Yeah. This is also the level where many experiments exist. So that can really be tested. And historically, especially important are interference experiments of neutrons and atoms in the gravitational field of the Earth. Yeah. So important, so historically important is the experiment by Colella, Overhauser, and Werner in 1975. So this is by the first letters known as the cow experiment. And so they used neutron interferometry in the terrestrial gravitational field. So really in the laboratory on a table. That's what is done. I will briefly describe it. And okay, you know that's the equivalence principle in Einstein gravity. So if you have something, we say a constant gravitational field, like on Earth, you can do also something with an acceleration. And this has been done. So experiment by Bonse and Wroblewski in Dortmund, not so too far from here, in 1983, and they have used accelerated systems instead of the gravitational field. Now the cow experiment, what is done there? Now, so you have here the beam of incoming neutrons, and then you have beam splitters A and B. So there's a beam splitter, and that's okay. It's in the gravitational field of the Earth, right? So that's the perpendicular direction, and then there's beam splitters, and okay, like that. So you have here C and D, and then you have detectors. So detectors. And okay, we call this here a height H0. And then we can rotate the whole apparatus around this angle. So of course, when it's up, then it's really perpendicular here. So at this height, no, but you can rotate it here, so it can also be horizontal, and so on. So you measure, so you have the neutrons, you let them interfere, and then you rotate that, and you measure the interferences independence on this theta. So theta equals 0 is horizontally orientated, and theta equals 90 degree is like it's here depicted vertically. So how do you describe it theoretically? Of course, as long as the neutrons are non-relativistic, as they usually are, then it's sufficient to use the Schrödinger equation. If they are relativistic, or you want to discuss relativity effects, you must use the Dirac equation. So the theoretical description is with the Schrödinger equation for neutrons in the gravitational field. And because, of course, we know from relativity that gravitational mass is equal to inertial mass, that's the equivalence principle, but it's also interesting to test it. So I mean, classically, we test the equivalence principle by torsion balance and other things. And also here, it's interesting to test it in a quantum regime. So we make an ansatz here for H with the two different masses. No? So we have here, I mean, the kinetic term p squared over 2mi. No? So this is the inertial mass. And then we have here the coupling to gravity through the gravitational mass. No? So in the limit of the laboratory, G is roughly constant. So that's the Newtonian, I mean, value for that constant gravitational field. And of course, this is the gravitational mass. I mean, more precisely, the passive gravitational mass, not the active one that generates the gravitational field. And we have also to use another term, because this is on the rotating Earth. And actually, the experiment is so precise that you can measure the rotation of the Earth by these interferences. So we have minus omega times L, where omega is the angular velocity of the Earth. So terrestrial angular velocity. And this is the angular momentum of the neutron with respect to the center of the Earth. Okay, so in my book you find the explicit calculation, and in case you're interested, I can show you this on one of the Thursdays following your request. Here I will not do that. Yeah, so in a sense it's standard quantum mechanical calculations of interferences. I will just give you the result for the interference fringes. So we have here a phase shift in interferometers, and I call this delta beta, which is defined of 1 over h bar, and then we have just the momentum dr. I mean, because that's what you have. I mean, you know that you have e to the I px basically in quantum mechanics, and you do that here in that parallelogram here of A, B, C, D here. So here. So you have to calculate the momentum. Well, actually I can write it down for you. The P is mi r dot, that's the kinematic momentum. And from that term, but you also have a contribution from that, which is plus mi omega r. No. And so, okay, if you first have this term, this comes from the rotation of the Earth, and if you insert numbers, about 2% of the whole effect, which is of course a smaller contribution, but a measurable one. And this is what gives rise to what is called the Sagnac effect. Well, this is in principle a classical effect from the 1920s with photons, but here it occurs for everything that is quantum. And so it's a delta beta Sagnac is 2 mi over h bar omega times a, the angular velocity of the Earth, and a is the absolute value is the area of this parallelogram, and the direction is the normal direction here. Yeah. So you see, you don't need anymore to construct big Foucault pendula to demonstrate the rotation of the Earth. In principle, you can do it here in an experiment of such a size and measure this. Although, of course, it's more impressive to see the pendulum than having interferences for which you need a lot of theory to understand. No, okay, that's from that. But here, from this, you have then the main. So this is about 2% of the whole effect. And this here leads then to something that is the gravitational effect, which turns out to be inertial mass times gravitational mass times g lambda a sine theta over 2 pi h bar squared. So, and what you see here, this is very important, is that here inertial mass and gravitational mass occur in a product. Now, and this is because here it's the p is the one that is quantized, right? And you have here in the denominator and here in the numerator. So it's not like in the classical equation of motion. If you have a classical neutron moving in the gravitational field, of course mi and mg can occur as a quotient, and if they are equal, then they just cancel, and you have universality of free fall. But here you see they occur as a product. This is why it's interesting to have a look at it in the quantum regime. One can show that if you rewrite this in terms of other quantities, observable quantities, that it's also as a quotient, but at least in this direct way it comes as a product. And yeah, the experiments are in full accordance, given the accuracy, with the equivalence principle. So equivalence principle, valid up to used accuracy. Okay, so this is certainly not yet quantum gravity, because the gravitational field is classical, but what you at least have here, I mean, you have here from g, of course, the gravitational constant, and here you have h bar squared. At least this combination enters, and for the first time in the lab that something has been measured where this combination enters, not g over h bar squared. But no surprises seem to have arisen from that. It's just a standard quantum mechanics. Later, so that's Newton interferometry. So later people have focused more on atom interferometry, because this is easier to handle, and also have checked that the equivalence principle holds up to order 10 to the minus 7 and better. Also, what people have done with neutrons since, for example, in Grenoble at the Institut Lagrange, was to throw neutrons, to the height, and let them fall. Of course, classically, that's okay, what you can do every time. But if you have a quantum mechanical object, a neutron, then of course you have also to solve the Schrödinger equation. If you solve the stationary one, so h psi e psi, and you find, of course, discrete values. So perhaps you know from your quantum mechanics course, if you have a linear potential, then you can also solve exactly the eigenfunctions and eigenvalues. There are these Airy functions and so on. And this has been tested. The ground state energy in the gravitational field of the Earth, it's of course much smaller than what you have in the hydrogen atom, where you have this 13.6 electron volt here. It's about a pico electron volt. But people already 20 years ago have measured these eigenvalues of freely falling neutrons in a gravitational field. Of course, if the neutrons move relativistically, then you have to use the Dirac equation. You find also some details in my book, because there are also some additional effects that come from special relativity, which I will not discuss here. But you can read about it, or I can tell you more about it. The full Dirac equation usually you do not need further discussion, but what is done is usually one has an expansion in powers of 1 over speed of light squared. So people from, say, who have heard advanced quantum mechanics know perhaps about a Foldy-Wutthuysen transformation. This is what is used here. And so there are some additional effects that at least some of them have been indirectly observed. Okay, so that was the first level. And so for the final thing for today is then the second level, which is quantum field theory in curved space-time. So this was one. So this is quantum field theory, QFT, and I call it the global structure of space-time. So there are new aspects, I mean, in addition to what we had on that level, the new aspects, of course, now have quantum fields, which are infinitely many degrees of freedom, not just a neutron, say, an atom. And there are also global aspects of gravity that can come from the curvature, but also from non-inertial motion. For example, if you have Minkowski space-time, but you have a uniform acceleration, you have so-called Unruh effect. So here we have new aspects from quantum fields. And from global aspects, it can be, I mean, so curvatures, global curvatures, curvatures also local, but I mean, you have in Einstein's theory many possibilities, curvature, but also acceleration in flat space-time. Now, when you usually learn quantum field theory, you learn about quantum field theory in Minkowski space-time, and you learn about it in inertial systems. That's what is the usual formalism. Because there you have then the so-called Poincaré group and the Poincaré transformation, which connects the various observers in inertial systems. But if you have external fields or non-inertial system, then you have processes like particle creation, because the concepts of vacuum and particles, they are defined with respect to the Poincaré group. So we have here, I mean, concepts of vacuum and particles. They are usually defined by the Poincaré group, because they're invariant with respect to that. So if you have one inertial observer and other with constant velocity, these two observers agree on the concepts of vacuum and fields. So I don't give here a lecture course on quantum field theory in curved space-time, where you have this Bogolubov transformation, all that. But I mentioned at least 2 or 3 important results, so that partly will play a role in the later chapters on black holes, for example. No? So especially so important effects. So there's I mean, the Hawking effect. Yeah, which we will discuss, or some aspects discuss in the chapter 7, that black holes actually are not really black, but they radiate with a temperature proportional to h bar, and you have h bar kappa over 2 pi kbc, no, with Boltzmann constant, and this is the surface gravity of a stationary black hole known from relativity, which is uniquely characterized by mass, angular momentum, and charge of the black hole. And so surface gravity. So at least on that level, of course, we don't have really experiments of that so far. I mean, there are discussions about analog gravity and so on, but at least we have a concrete prediction. And so surface gravity, so for Schwarzschild, we have kappa is c to the 4 over 4 gm, which you can write as gm over the Schwarzschild radius squared. No? So it looks really like Newtonian gravitational acceleration. This is why it's called surface gravity. And in the Schwarzschild case, okay, then you have T BH is h bar c cube over 8 pi kbc times 1 over m. which numerically is around 6.17 times 10 to the minus 8 solar mass over m Kelvin. So you see it's very small. This is why it's so difficult to measure. But you also see that all the relevant constants fundamentally occur here, right? The h bar, the c, and oops, this is a typo here. So here, of course, should be g and the g. Yeah. So as they occur in the Planck units. And the only parameter is here the mass of the black hole. This is here in the denominator, so the black temperature increases if the mass decreases. So if you had very small mass black holes, you could see the effect. But that's the question about whether such small mass black holes exist. I say some words in the chapter 7 about that. So you see here, we have here temperature, so thermal effects combined with here gravity effects. So in a sense, this is analogous to the Preuss relation. E is h bar omega and P is h bar k, where also quantities from mechanics are related to quantities from, say, wave theories. Now, I mentioned that here also you have an effect about in the case of acceleration, and this is what this usually called the Unruh effect. No, so Hawking did that in 1974, and Unruh, actually this was discovered a little bit later, and actually was motivated by Hawking's effect. And so we have here the temperature as h bar a over 2 pi kbc, now where this is the constant linear acceleration of an observer through Minkowski vacuum. And so this numerically is about 4.05 times 10 to the minus 23. A measured in centimeters per second squared and Kelvin. So you say, okay, that's also unmeasurably small, such a small temperature if you measure that. But if you look more precisely into numbers, say in accelerators, in principle you can have here even very high temperatures. But the problem is, to have here, this refers to linear acceleration, and to have a high linear acceleration. So for the circular case, for example, there's, okay, you don't have this result, but other results, they have been checked or tested, but this particular effect, this thermal effect, this has, to my knowledge, not yet been clearly seen, although people try, say, with strong lasers and also linear accelerators to measure this. And you see here that here kappa and A, they have the same dimension, occur at the same place. So this is not an accident, that this looks so similar. So they are in a sense related by the equivalence principle. So you see here kappa and A. Okay, so the last effect is something that will be relevant in cosmology, maybe later. We discussed a bit, which is quantum field theory in de Sitter space. So believe that the early universe underwent a period of at least quasi-exponential expansion, so-called inflation, and that there are quantum fluctuations there, and in this inflation that they will become, well, they assume classical properties through decoherence and other effect, and they will lead to the power spectrum that we observe in the CMB. So power, so CMB power spectrum. So if we, from inflationary cosmology, so we'll have, okay, there are numerical things, and the power spectrum has to be defined. There are certain two-point functions. It's not the place here to discuss that, but typically you find here something like a Planck time times Hubble parameter of inflation. So Hubble parameter of inflation squared. I mean, this has dimension 1 over time, this has time. So you see that also the Planck scale enters here. And if you're very, in a sense, courageous, you can call, because this has been measured, you can call this already an observed effect of quantum gravity. I say something more about this. I mean, it's based on a linearized theory of the gravitational field, which we will discuss in the chapter 2. But at least in a certain sense here, you have a quantum gravity effect here too. Okay, this so much for the section 1.1. So next time will then be the second part of chapter 1 of the motivating chapter, and mainly will be subsection 1.2. So I will discuss, say, in principle, alternative to quantum gravity, a so-called semi-classical theory, where in the Einstein equations, which are g mu nu, say, now without a cosmological constant equal to me, if this becomes an operator, of course you cannot have it that way, that you write this here. Now that would be something that you would say is very natural. And so this I discuss a little bit next time, and also its problems. And then I will jump to full quantum gravity, first give you a conceptual overview of what will to become, before then in 2 weeks we will enter the first approach. So thank you for today, and bye-bye.